Welcome to a video that will show how to determine where a curve defined by a vectored valued function is smooth. First, a smooth curve does not have any sharp corners or points, so here are some examples of curves that are completely smooth. Again, notice there are no sharp corners or points on any of these curves, whether it's a plane curve or a space curve. So a vector valued function is going to produce a smooth curve on a given interval if the derivative of the vector valued function is not equal to the zero vector. So if we have a vector valued function r of t that has an x and y component or an x, y, and z component, then if the derivative at that given value of t does not equal 0 for each component, then that curve will be smooth. The point where a curve has a sharp corner or point is called a cusp or a node. So looking at this curve here, you can see there are several places where this curve has a sharp point or corner, as we see here, 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 and so on, and these are called cusps or nodes. And these will occur where each component of the derivative of the vector valued function will equal 0. And anywhere in between these values it would be smooth. So what we're going to do is determine where the derivative of the vector valued function is equal to 0. That'll give us where the nodes occur. And then the intervals of t in between these values will be where the curve is smooth. Let's go and take a look at an example. Here we want to determine the intervals to which the given curve is smooth on the closed interval from 0 to 2 pi. I provided the graph here so that we can tell there are going to be places where this curve has a sharp corner or point. So what we'll do here is determine the derivative of this vector valued function, set the derivatives of each components equal to 0, and then determine for which values of t both the x component and the y component of the derivative would be equal to 0. So it may be helpful to rewrite this in a form that's easier to find the derivative, meaning I'm going to write this as 3 and then cosine t to the third power. This will remind me to apply the chain rule when I find the derivative, and the y component will be 3 times sine t raised to the third power. Okay, let's go ahead and find the derivative of this vector valued function. Remember, that means find the derivative of each component. So cosine t is actually going to be our u when we apply the chain rule. So we're going to multiply by this 3. That'll give us 9 u to the second times u prime, or 9 cosine squared t, and then times u prime. The derivative of cosine t is going to be negative sine t. Now for the y component, again, we have to apply the chain rule here, where sine t is equal to u, and u prime will be cosine t. So we're going to have 9 sine squared t times cosine t. Cosine t is u prime. Let's go ahead and clean this up. This is going to be equal to negative 9 cosine squared t times sine t. Then we'll have 9 sine squared t cosine t. And again, we want to know when this is equal to the 0 vector, so where the x component and the y component are both equal to 0. So what that means is we want to determine when negative 9 cosine squared t sine t is equal to 0, and when 9 sine squared t cosine t is equal to 0. So we want the value of t where both of these equations would be equal to 0 at the same time. Now remember, to solve these trig equations, we want to have it in terms of one trig function. So using the identity cosine squared plus sine squared equals 1, we can replace cosine squared t with 1 minus sine squared t. So we'd have negative 9 times 1 minus sine squared t times sine t equals 0. And over here we can replace sine squared t with 1 minus cosine squared t. So using this equation here, we want to know for what values of t would 1 minus sine squared t equal 0, and when would sine t equal 0. And over here we want to know when 1 minus cosine squared t is equal to 0 and when cosine t is equal to 0. Let's go ahead and move the sine squared to the other side. We want to know when 1 equals sine squared t. So if we square root both sides, we want to know when plus or minus 1 is equal to sine t. So on the interval from 0 to 2 pi, sine t would be equal to 1 at t equals pi over 2, and sine t would be equal to negative 1 at 3 pi over 2. And then for sine equal to 0, that's going to occur at 0, pi, and 2 pi. Now this isn't enough information to determine where these nodes or cusps occur, because these equations here and these equations here must be 0 for the same values of t. So let's go ahead and solve these equations. Let's go ahead and add cosine squared t to both sides. So we have 1 equals cosine squared t. Again, we're going to square root both sides of the equation. So we want to know when plus or minus 1 is equal to cosine t. Well, cosine is equal to 1 at 0 and 2 pi, and cosine is equal to negative 1 at pi radians. And then cosine t is equal to 0 at pi over 2, and also at 3 pi over 2. And in this case, note that the values of t that make the x component of the derivative equal to 0, and the values of t that make the y component of the derivative equal to 0 are all the same. That's not always the case, but it is the case here. So these are the values of t where the derivative of the vector valued function is equal to the 0 vector. So all the values in between these, the curve would be nice and smooth. So let's go ahead and take this information onto the next screen. We had t equals 0, t equals pi over 2, t equals pi, 3 pi over 2, and 2 pi. So that means the curve will be smooth on the intervals between these values. So it'll be smooth on the open interval from 0 to pi over 2, and then from pi over 2 to pi, from pi to 3 pi over 2, and then lastly from 3 pi over 2. Now keep in mind these intervals are intervals of t, not x like we normally think of when we're talking about rectangular equations. I hope you found this helpful. Thank you for watching.